Hi friends, welcome back to my YouTube channel. So today I am going to discuss about error control, the fourth part. Ignore this part 3 mentioned in this slide. This is the fourth part of the error control. So this is from module 2, Computer Communication EC 407 from KTU syllabus. EC Electronics and Communication Engineering subject. And this topic is all based on the KTU syllabus. So if you are a KTU or Btech student from KTU, so you can refer these notes and this video for your exam. And let's go to the video. So we have already discussed linear block codes and other Hamming codes, parity check, symbol parity check, error correction and error detection. So now we are going to discuss about cyclic codes. So this is follow to that previous video, so you can start from the beginning and then get this one, and you can learn this one also, so you will get an idea what it is. So cyclic codes are a special linear block codes with an extra property. So in a cyclic code, if a code is cyclically shifted, rotated, the result is another code word. So what is the extra property means? If the cyclic code it is cyclically shifted or rotated, it will give a result that is another code word. So for example, if 10110000 is a code word and we cyclically left shift, then 01100001 is also a code word. So in this case, we call the bits in the first word A0 to A6 and the bits in the second word B0 to B6. We can shift the bits by using the following. In the rightmost equation, the last bit of the first word is wrapped around and becomes the first bit of the second word. So you can see the equation: B1 equal to A0, B2 equal to A1, B3 equal to A2, B4 equal to A3, and B5 equal to A5, and B6 equal to A5, and B0 equal to A6. So when it is left shifted, one bit wise it will be rotated in the second word also. So cyclic redundancy check means we can create a cyclic code to correct errors. So to correct errors, we can create cyclic codes. So we simply discuss a category of cyclic code called cyclic redundancy check, that is CRC, that is used in networks such as LANs and WANs. So table 1 that you can see in the next slide. So data word and code word, and data word and code word are there. So first one is a 4-bit data word and other one is code word is 000 and 7-bit code word is there. So we can go to the table 1 shows an example of a CRC code. We can see both the linear and cyclic codes of this code. So in this encoder, the data word has k bits. K bits means 4 here, and the code word has n bits, that is 7. And the size of the data word is augmented by adding n minus k 3 here, zeros to the right hand side of the word. The n bit result is fed into the generator. So here we are adding 3 zeros to the right hand side of the word, and we will get a code word of 7-bit. So first 2 columns we have the linear block codes, and second thing we will have the rotated CRC codes. So the generator uses a divisor of size n minus k plus 1, that is 4 here, predefined and agreed upon. The generator divides the augmented data word by the divisor modulo 2 division, and the quotient of the division is discarded and remainder is R2, R1, R0 appended to the data word to create the code word. So here we will get a quotient because the augmented data word is divided by modulo 2 division, and we will get a remainder of R2, R1, R0 and appended to the data word to create the code word. So the decoder receives a possibly corrupted data word. So a copy of all n bits is fed into the checker, which is a replica of the generator. So the remainder produced by the checker is a syndrome of n minus k, that is 3 here bit, so which is fed to the decision logic analyzer, and the analyzer has a symbol function. If the syndrome all bits are 0, the 4 leftmost bits are code word are accepted as the data word, interpreted as no error, otherwise 4 bits are discarded. That is an error. So the figure shows the exact explanation that I have given now. So sender and receiver is there. Sender and receiver is there. This is the receiver, and data weight is A3, A2, A1, A0, and data weight here it is A2, A3, A1, A0. So we have given 3 zeros are added to the data weight, and we are giving the code weight to the generator, and it is dividing by the modulo 2 divisor, and we will get R2, R1 and R0 as the remainder, and A3, A2, A1 and A0 is the data weight. So the divisor is D3, D2, D1, D0. So this is divided here, and this code word is transmitted to the decoder, and decoder will be the B3, B2, B1, B0, Q2, Q1, Q0, and there will be a checker function, and checker function will check with the divisor and the code word. So it will generate a syndrome of S2, S1 and S0, and there will be a decision logic. If the syndrome is all 0, then the data weight is accepted. If it is not, then the data weight is discarded. So this is the overall working of cyclic redundancy check. So this is used for error correction, and for example we are looking into one example. So for the encoder part, let us take a closer look to the encoder. The encoder takes the data weight and augmented with the n minus k number of zeros. It then divides the augmented data weight by the divisor as shown in figure 1. So the process of modulo 2 binary division is the same as the familiar division process that we use in decimal number. So the modulo 2 binary division is similar to our division in decimal numbers. So in this case, addition and subtraction are the same. So we use XOR operation to do both. So here we are using XOR both in the addition and subtraction. So as the decimal division of the process is done by step. In each step, a copy of the divisor is XORed with the 4 bits of the dividend. So the result of the XOR operation remainder is 3 bit in this case. So which is used for the next step after one extra bit is pulled down to make it 4 bit long. So here is an example. So if you see, the data weight is 1001 and data weight is divided by divisor is 1011, and we are dividing it, divider is 1011 and 1001 is the data weight, and we are adding 3 zeros to the right side, and so this is we are adding because we need to make it at 7-bit data weight code weight, and we are dividing it. So here we are doing 1011. So first we are doing it is like 11 minus, it's a addition and it's a multiple addition and subtraction happening in this division action. So 1 minus 1 will be 0. So because it is XOR operation, so if the data bits are same, then the resultant will be 0. If the bits are different, the resultant will be 1. So 1 1 will be 0, and 0 1 will be 1, and 0 0 will be 0, and 1 1 will be 0. So that we can ignore, and we need to take the 1 0 from the upper, that is the augmented data weight, that 0 0 0. From there we are getting 1 0 to the below side, and we will get 0 1 0 0. So here we are adding. So what happened, we need to like, so if like why we are getting this 1011 here, so the quotient, so we need to multiply. So another point we need to make sure that, so in this division, if the leftmost bit of the dividend as part used in each step is 0, the step cannot use the regular divisor, we need to use all as a 0 divisor. So here if you see, the left side part is 0 of the dividend. So left side part is dividend value of the left side part is 0. So we need to use the divisor as all 0. So here we got in the first step we got one answer, that is 0 1 0 0, and we need to use 0 0 0 0 as the divisor next step, because since the leftmost bit is 0. So here we will get 0 0 will be 0, 0 0 will be 0, and 1 0 will be 1. So here the leftmost bit is not 0, so we can use the same number, that divisor is 1 0 1 1. We can use the same thing here, and also from the augmented data word we can choose 1 0 to the down. So there we will get 1 0 1 0 1 0 0 0 minus 1 0 1 1. So this will be, the output will be 1 and then 1 and then 0, and again we will need to give the 0 to the down, and then the leftmost bit is 0, and we need to use the 0 0 0 as the divisor, and we will get 1 1 0 as the remainder. So the code word is, as I suggested, as I discussed later, the code word is A3 A2 A1 A0 and R2 R1 R0. So encoder will transform the code word as 1001 1110. So this is a reminder and this is the data word. So this is happening here. So in the encoder side we are almost kind of completed. So decoder side we can discuss like that. Decoder can change during the transmission. The code word can change during transmission. The decoder does the same division process as the encoder. So the remainder of the division is the syndrome. Remainder of the division is the syndrome. So if the syndrome is all 0, then there is no error and the data word is separated from the received code word and accepted, otherwise everything is discarded. So figure shows two cases. The left hand figure shows the value of syndrome when no error occurred and the syndrome is 0 0, and the right hand part of the figure shows the case in which there is one single error in the syndrome is not all zeros, that is it is 0 1 1. So if you see here, our code word is, our data word is 1001 and our augmented value, our encoder gives one code word to the decoder, that code word is 110, and we are dividing it by 1011 and we will get a syndrome of 0 0 0, and this syndrome is all 0, so that data word is accepted. And in the next case the the code word is 1000110, so there is one error. So if you go by the same method that we discussed, we will get a syndrome of 011. So there is one error in the first bit, so that we are ignoring or discarding this bit from the sender. So this is the process that we are using in the cyclic CRC, cyclic check redundancy, cyclic redundancy check. And the divisor, you may be wondering how the divisor 1011 is chosen. So but in general it involves abstract algebra, so we can discuss it. So it is just an example. So if you are writing an example, you can take this similar example like this. So you can write this similar example like this. So polynomials, a better way to understand cyclic codes and how they can be analyzed to represent these polynomials. Again, the section is optional, so a pattern of zeros and ones can be represented as a polynomial with coefficient of 0 and 1. So the power of each term shows the position of the bit and the coefficient shows the value of the bit. So as you know, we can represent each polynomials as a power of zeros and ones and represented by the coefficients of 0 and 1. So there is a word like A6, A5, A4, A3, A2, A1, A0 as 1 0 0 0 0 0 1 1. So if you go by this, 1 into x raised to 6, 0 into x raised to 5, 0 into x raised to 4 plus 0 into x raised to 3 plus 0 into x square plus 1 into x raised to 1 plus 1 into x raised to 0. So this will be goes to 1 into x raised to 6 plus x raised to 1 plus 1 into x raised to 0, that is already 1. So the short form x raised to 6 plus x plus 1. So this is the polynomial that we can represent each of the term by polynomials with the coefficient 0 and 1. So degree of polynomial, the degree of polynomial is the highest power of the polynomial. So in this example, the highest power of the polynomial is 6. So note that the degree of polynomial is 1 less than the number of bits in the pattern, and the pattern is in this case has 7 bit. So the pattern have 7 bit, but so that's why the degree of polynomial is 1 less than the number of bits in the pattern. 1 less than the number of bits in the pattern. So that means it will be 6. So adding and subtracting polynomials. So adding and subtracting polynomials in mathematics are done by adding or subtracting the coefficients of terms with the power, same power. So in our case, the coefficients are only have 0 and 1. So adding is modulo 2. So these two has two consequences. First, addition and subtraction are the same. Second, adding or subtracting is done by combining terms and deleting pairs of identical terms. For example, adding x raised to 5 plus x raised to 4 plus x raised to 2 and x raised to 6 plus x raised to 4 plus x raised to 2 just gives x raised to 6 plus x raised to 5. Since x raised to 2 is common in both, so it will be discarded. The same pairs is discarded, and terms x raised to 4 and x raised to 2 are deleted. X raised to 2 pairs are same, so we will get a resultant as x raised to 5 and x raised to 6. However, note that if we add, for example, 3 polynomials and we will get x raised to 2 3 times, we delete the pair of them and keep the third. Okay, so in the subtraction mode, we are discarding same polynomials, same terms. So here x raised to 4 and x raised to 2 are the common, so we will discard that and we will get a remainder. We will get a output as x raised to 5 plus x raised to 6. So in addition, we will get x raised to 5 plus x raised to 6 plus 2 into x raised to 6 plus 2 into x raised to 2. So we will get 2 raised to x as 3 times, and we delete the pair of them and keep the third. So that will be the output. So multiplying or dividing terms, multiplying a term by another term is very simple. We just add the powers. For example, x raised to 3 into x raised to 4 will be x raised to 7. For dividing, we just subtract the power of the second term from the first term by, so x raised to 5 by x raised to 2 will be x raised to 3. So multiplying two polynomials, multiplying two terms, one is by another by term by each, the polynomials must be multiplied by all other of the second. So the resultant, of course, is then simplified and the pairs of equal terms are deleted. The following is an example. So x raised to 5 plus x raised to 3 plus x raised to 2 plus x and x raised to 2 plus x raised to 1 plus 1. So we need to multiply each terms by each from the other term. So we will get a resultant. So this is the same as the our normal mathematics. So dividing a polynomial by another. Dividing a polynomial by conceptually the same as the binary division we discussed in the encoder. So we divide the first term of the dividend by the first term of the divisor and get the first term of the quotient, and then we multiply the quotient of the divisor and subtract the resultant from the dividend. We repeat the same process until the dividend decrease is less than the divisor decrease. So shifting is the binary pattern is often shifted a number of bits to the right or left. Shifting to the left means adding extra zeros as rightmost bits. Shifting to the right means deleting some rightmost bit. So shifting to the left is accomplished by multiplying each term by polynomial x raised to m, where m is the number of shifted bits, and shifting to the right means accomplished by dividing each term by polynomial x raised to m, dividing and multiplying. So the following shows the shifting to the left and shifting to the right. Note that we don't have any negative power in the polynomial representation. Shifting left 3 bits, 1 0 0 1 1 becomes 1 0 0 1 1 0 0 0. So we will get x raised to 4 plus x plus 1 becomes x raised to 7 plus x raised to 4 plus x raised to 3. So shifting right 3 bits, 1 0 0 1 1 becomes 10. That means x raised to 4 plus x plus 1 becomes x. So this is very simple. You can check this in your own way. So when we augmented the data word in the encoder as figure 1, we actually shifted the bits to the left. Also, in order that we can concatenate 2 bits pattern, we shift the first polynomial to the left and then the second polynomial. So cyclic code encoder using polynomials. So now we can have discussed the polynomial operation. Now we show the creation of a code word from a data word. So figure shows a polynomial version of figure 1, and we can see that the process is shorter, and the data word 1001 is represented as x raised to 3 plus 1, and the divisor is 1011 is represented as x raised to 3 plus x plus 1. To find the augment, the divisor is 1011 is represented as x raised to 3 plus x plus 1. To find the augmented data word, we have left shifted the data word 3 bits, multiplying by 2, and the resultant is x raised to 6 plus x raised to 3. And the first term is of the quotient is then x raised to 6 by x raised to 3 or x raised to 3. Then we multiply x raised to 3 by the divisor and subtract according to our previous definition of subtraction the resultant from the dividend. The result is that with the degree greater than the divisor degree, we continue to divide until the degree of the remainder is less than the degree of the divider. This is the same process, only the change is we are changing the numbers, the binary numbers into polynomials, and we are doing the process same. Multiple addition and subtraction is doing there, and we are getting a remainder, and this combining this code word, we will get the same code word as we discussed in the encoded part. So you can choose this in your you can try this in your work, so you will get an idea. So this is the same, this is simple subtraction and addition and multiplication and division. So this can be seen that the polynomial representation can easily be simplified, the operation of the division in this case, because the 2 steps involving all zeros divisor are not needed here. Of course, one could argue that all the zeros divisor step can also be eliminated in binary division. So in the polynomial representation, the divisor is formally referred to as generator polynomial. So the divisor in a cyclic code is normally called generator polynomial or simply the generator. So the polynomial CRC8, so there is an example for the polynomials that are used in the different application: CRC8, CRC10, CRC16, CRC32. So 8 is used in ATM header, 10 is used in ATM AAL, 16 is used in HDLC, and 32 is used in LANs. The good polynomial generator needs to have the following characteristics. It should have at least 2 terms. The coefficient of the term x raised to 0 should be 1, and it should not divide x raised to t plus 1 for t between 2 and n minus 1, and it should have the factor of x plus 1. So this is a behavior of a good generator, needs to have these characteristics. And advantages of cyclic codes, we have seen that the cyclic codes have a very good performance in detecting single bit errors, double errors, and odd number of errors and burst errors. So they can easily be implemented in hardware and software. So they are especially fast when implemented in the hardware. So this has made the cyclic codes a good candidate for many network. And other cyclic codes have discussed in the sections are very simple. To check the bits and syndromes can be calculated by simple algebra. So there are, however, more powerful polynomials that are based on the abstract algebra involving Galois field. and one of the most interesting of these codes is Reed-Solomon code, used today for both detection and correction. So this is for this, all section is optional for you, so you will get an idea how we can do the actions or do the analysis. So that's why I included in this portion. So you can check this, maybe this will ask in the question exam. You can refer this information also, this will be very helpful for you. So if you like this video, please subscribe my channel, like, share and comment. So thank you for watching my video. So if you have any queries or questions, just put in the, please let me know and put in the comment box. I will definitely answer your queries. So thank you once more. So see you in the next video. Thank you.